Okay, imagine staring into the darkest abyss in the universe, only to realize it's staring right back, hiding secrets that literally rewrite astrophysics. Welcome to This Explainer. Today, we're diving deep into the ultimate cosmic heavyweights, black holes. We're going to break down their extreme anatomy, the violently bizarre physics of spaghettification, and a brand new, totally mind-bending discovery from the James Webb Space Telescope. Trust me, you'll want to stick around for this one. Here's our roadmap for today. First up, the anatomy of a black hole. Second, the noodle effect. And finally, Webb's little red dots. Let's get right into it. Section 1, Anatomy of a Black Hole, also known as the cosmic vacuum. So a black hole isn't just, well, an empty void of nothingness. It's actually this incredibly chaotic, highly active system. Right at the boundary, you've got the event horizon. That's the ultimate point of no return, where the escape velocity is literally faster than the speed of light. But just outside that edge, pure, unadulterated chaos. You've got the accretion disk, this incredibly fast spinning disk of doomed, superheated matter. Then there's the corona, a billion-degree cloud of particles, and these massive particle jets blasting out at near light speed. And all of this surrounds the singularity, the exact center where our current laws of physics just completely break down. Now, if we zoom in just a bit closer to that event horizon, things get really trippy. We hit something called the photon sphere. Basically, the black hole is so massive that it warps the very fabric of space-time. It warps it so severely that it actually forces passing light to orbit it. Yeah, light rays literally travel in circles around the black hole, looping multiple times before finally shooting off toward our telescopes. It creates this massive, highly distorted optical illusion of bright rings framing a pitch-black shadow. And that intense warping triggers another really weird visual quirk: Doppler beaming. See, because that accretion disk is spinning at blistering speeds, relative physics kick in. It creates this crazy visual siren effect. The light on the side of the disk racing toward us gets supercharged, it's amplified and shifted to a much brighter blue. Meanwhile, the side spinning away from us fades into this dimmer, darker red. So visually, a black hole actually has a super lopsided, glowing appearance. All right, moving on to Section 2, the noodle effect, surviving the extreme. Now we have to talk about the ultimate space thought experiment. The question every space enthusiast asks: what exactly happens to your body if you accidentally cross that point of no return? Well, I hate to break it to you, but it's not great. The actual scientific term for your demise here is spaghettification. And yes, Stephen Hawking himself coined that one. Here's why it happens. Gravity operates on an inverse square law. Basically, the closer you get, the stronger the pull, and it ramps up unbelievably fast. So, say you fall in feet first. The gravitational pull on your feet is vastly, vastly stronger than the pull on your head. As a result, you get violently stretched out vertically, while your sides are being crushed horizontally. You are quite literally drawn out into a long, thin string of cosmic spaghetti. But here is where the physics gets super counterintuitive. It all depends on the scale of the black hole. If you fall toward a tiny stellar mass black hole, the gravitational gradient is super tight. The tidal forces are so vicious you'd be spaghettified long before you even reach the event horizon. But if you fall toward a supermassive black hole, like the monsters at the center of galaxies, it's so huge that the curve of gravity at its horizon is actually pretty gentle. In theory, you could slip right across the threshold of a supermassive black hole completely intact, without feeling any pull at all. I mean, sure, it's still a one-way trip to your doom, but the bigger the black hole, the gentler the edge. Wild, right? Which brings us to Section 3, Webb's little red dots, a modern astronomical mystery. So recently, the James Webb Space Telescope peered way, way back to the dawn of the cosmos, and it found something that straight up panicked astronomers. It beamed back images of these tiny, compact, little red dots scattered all over the early universe. At first, scientists thought they were looking at impossibly dense galaxies packed with old, mature stars. But that made no sense. They existed way too early in time to be that developed. It completely shattered our models of cosmic history. The panic was so real, scientists actually started calling these things universe breakers. But thankfully, we didn't have to throw our physics textbooks in the trash just yet. A new interpretation came along that explains this data perfectly: the black hole star. Scientists now realize these dots aren't impossible galaxies at all. Instead, they're rapidly feeding young black holes, totally wrapped up in a thick cocoon of dense gas. As the black hole sucks in matter, it unleashes a massive amount of energy. But that thick gas envelope traps the energy, scatters it around, and re-emits it. The final result? a smooth, thermal glow that perfectly mimics the light of a star. It's literally a black hole wearing a stellar disguise. To prove this, astronomers pointed the Webb telescope at one specific little red dot named GLIMPSE-7775. Now, this thing is 1.8 billion years. That is how far back in time after the Big Bang we are looking. Thanks to a massive galaxy cluster acting like a giant cosmic magnifying glass, Webb was able to stare at this one tiny speck of light for 80 hours. And it paid off. They found over 40 distinct chemical clues, including an iron forest of high-energy emission lines. It absolutely definitively confirmed there was a powerful, hidden black hole engine firing away inside that glowing cocoon. So, how does this fit into the grand scheme of cosmic evolution? Well, by combining Webb's infrared data with X-ray data from the Chandra telescope, scientists pieced the timeline together. Step 1. A young, hungry black hole is completely buried in a thick cocoon, blocking its X-rays and making it look like a little red dot. Step 2. As it eats, it starts aggressively clearing out the gas in its immediate neighborhood. And finally, Step 3. The cocoon breaks wide open, the disguise falls apart, and all those intense X-rays blast out into the universe. And suddenly, we see the bright, active quasar that we're all familiar with. And all of this brings us to a really profound realization. Think about it. If impossibly dense galaxies that threaten to break the universe turned out to just be young black holes wearing clever disguises, what else is out there? What other reality-bending mysteries are just hiding in the deep universe, waiting for us to finally decode their light? Honestly, as we peel back the layers of space and time, the anatomy of the cosmos just gets weirder and so much more wonderful. Thank you so much for joining me on this explainer today. Keep looking up, stay curious, and I'll catch you next time.